Hello, today we'll talk about fault detection. And once again, we will approach this problem as a state estimation problem. Today we will explore the use of a Kalman filter, so a standard linear Kalman filter, for fault detection in a thermal system. So we're going to measure temperature and detect if there is something going on with that system. And we'll start talking about modeling. We'll design a filter. Then we will try to find the suitable covariance matrices for the Kalman filter using maximum likelihood estimation. And then finally we will monitor the prediction error. We will monitor the C-score of the prediction error and use that to detect faults. And we will take a fault to be something like a faulty sensor. Maybe it gives a corrupt reading. Or maybe there is just an unexpected temperature fluctuation that we wouldn't really expect to see under our model, and we will treat that also as a fault. So we will look at plots that look like this one here today, and I will describe exactly what we see here in more detail later. But we have some state we're estimating, 2 state variables here on top, and we have some measurements and some predictions by the model in the plot below. So this is just as a teaser for now. To get some data to use, we will load a data set from Kaggle, so it's available on this link here. I have read the file, it's a CSV file, and we show some of the entries here. It has 62,000 entries. And we start by looking at it. It has 3 columns. It has a value, so this is the temperature we're interested in. I would guess that it's in centigrade. It has a sensor ID, it's always number 1, so we don't care about this one. And then it has a column of timestamps. And we see here that the timestamps are completely out of order, so we would have to sort them eventually. I create a date format string so that I can parse the timestamp strings as Julia datetime objects. And I do that here. So now I have a vector of unsorted timestamps. Then in order to sort them, I compute the permutation using sortperm. So instead of sorting the array, it gives me the permutation such that if I index with this permutation, I get the sorted array. And the reason I use this is because I want to use this permutation to sort not only the time vector, but also the temperature vector. So I create a sorted time array, and then I create a sorted temperature array, and I call that Y because that's my measurement. Right, so we have a bunch of measurements and time points available now. We'll look at the data. I plot it here. It's a function of time only. We see that it spans 1 year from 2016 August here to 2017 August. And we see that the temperature is usually between 0 and 40, whatever unit was used. I believe it's centigrade. And we see that this looks like an outlier. I can't tell you for sure that it's an outlier, but it's certainly something that is different than the rest of the data. We also see that there are some jumps here. So there is some data available here, and then there is no data available until here. So there are lots of missing data. And we will have to treat that. So that's an interesting challenge that often appears in practice. So to make this vector of time points a bit easier to work with, I convert them to a numerical value. So they were timestamps before, and if I call this dates.value, I now have a numerical value, and that gives me a value in milliseconds. So I divide by 1,000 here to get it in seconds. So I said that there were some missing data. So to explore a bit more in what way the data is missing, I plot the difference between consecutive time values here. And we see, I get a plot that looks like this. And we see that there appears to be a certain number of, or certain intervals present, but not others. So we see the smallest interval present in the data, it's 300 seconds. So that appears to be the base sample interval. But sometimes we see I have 900 seconds, so that's 3 times the base interval. And here I compute all intervals present in the data. And I can compute, if I divide by the smallest interval, I see that I only have integer multiples of the smallest interval. So that means that we record at a certain fixed interval, 300 seconds, but sometimes we just don't have a recording. Sometimes we have skipped one, sometimes we have skipped two, and so on, and sometimes we have even skipped 6,000 recordings. So that's obviously going to be an interesting challenge that we have to deal with. All right, so I extract this sample base interval into the TS variable, and TF is the length of the entire data set. I create a vector of, I call it here time full. So to facilitate working with this data set, it's not nice to have arrays where the interval between them, the time interval between recordings is different. So I create what I call a full time vector that includes all the time points in between, even if there is no data. And then I compute which indices of these time points are actually available in the data set, so that I can create a numerical vector of temperatures that has equidistant sampling. So it's sampled every 300 seconds. But if there is no data available in my CSV file, I just insert the missing value instead. And that will make it much easier to work with when I perform the filtering. All right, so to perform the state estimation using a Kalman filter, we need, of course, a model. And a simple model of a temperature thermal system is that the temperature derivative, T, is proportional here with a proportionality constant alpha to the difference between the current temperature and the temperature of the environment. So if the temperature is, it should actually be, alpha is negative here. If the temperature of the environment is higher than the current temperature, then we tend to increase in temperature until we approach the temperature of the environment. But then there might also be some external kind of energy being pumped into the system or extracted from the system. So if we think about the house, maybe the sun is shining in through the window, so that would add some disturbance that cannot be captured by the temperature of the environment. Or maybe someone opens the door or whatever and some cold air comes in. So when we looked at the temperature plots in the graphs above, we saw that the temperature doesn't appear to be just random noise. Instead, it varies smoothly like this up and down. And that's probably because the environment temperature, or this disturbance term here, varies slowly. So if I had just used this first order model in my Kalman filter, then this would have to be treated as Gaussian white noise. But we know that Tn and W together do not appear to be Gaussian white noise. Instead, they appear to vary slowly. So we would like to incorporate that knowledge into our model as well. And one way of doing that is to introduce an additional state variable. I call it here Z. So we say that the total model with two state variables is it's a double integrator. There is some noise W that affects Z, and that's being integrated, and then Z affects the temperature, and that's being integrated. So that's a double integrator, and we will see how well that works. So this is a linear model. We can write it on this form here. So this is now in continuous time. So the derivative of our state is some linear function of the current state and these noise inputs. So here we don't have any control inputs like we have had in previous videos. So this is now just a noise input. And the A matrix here in this case, we see that T does not depend on itself here. It depends on Z. So we have 0 and 1. And Z does not depend on anything but the noise. So we have zeros in the second row. And if we discretize this using a zero order hold assumption of the noise for simplicity, we get this A matrix here. And this is the A matrix associated with a discrete time double integrator with unit sample intervals. So if the sample interval had been something else, we would have some TS here. All right, so this would be the dynamics matrix we used in our model. And I define those matrices here. Here is the A matrix. SA here just means that it's a static array, and I use that for performance reasons. The B matrix here is just the zeros, the traditional input matrix, since we don't have any control inputs. The C matrix is 1, 0, so that means that we can measure the temperature, but we can't measure this kind of hidden internal state that I introduced called Z. And we don't have any direct terms since we don't have any inputs. And then we need to pick some covariance matrices for the Kalman filter. And since we're using a double integrator, we call the function called double integrator covariance. And that returns the matrix on a very particular form that is suitable for a double integrator, and I scale that with some value I have chosen. I picked that by simply looking at some plots, and we will see a much more principled way of finding this value towards the end of this video. And then for the measurement covariance, I also pick something that looks reasonable. So we have 0.1 degree resolution in our temperature measurements. So this is chosen kind of to reflect that roughly. It doesn't matter if it's exact or not, because it's only the ratio between those two that matters for a linear Kalman filter, and we will optimize one of them eventually, so the value of the other one doesn't matter that much. Then we also pick an initial estimate distribution, so the estimate of the initial condition. And here I say that the temperature state is given by the first measurement, and we say that this velocity variable Z, we guess that it starts at 0. And then I pick a very large covariance because I say I don't actually know what the initial state is of this system. So this is probably a reasonably good guess, but I still pick a very high value because I will actually start filtering at different points in the trajectory to have small plots with not too much data. So it's reasonable to have a large covariance here. And then I package all the matrices, dynamics and covariance into the Kalman filter structure. And we see that it now includes a bunch of matrices that are static matrices, so that's good for performance. All right, then I want to perform the filtering. And here, since I have a bunch of missing data, I have implemented a special forward trajectory function. So forward trajectory is a function from the particle filter library that just performs filtering along an entire data trajectory in one go. And here I call it special because I want to do something particular if I encounter a missing data point. So here I create a bunch of arrays so I can store the solution. And then I loop over all the time points in the data. And if there is any missing entry in the measurement, so if the measurement is missing, then I avoid doing the correction step because I don't have any measurement to correct with. But if there is nothing missing, then I call the correction step of the Kalman filter, and I compute the Z score. So the Z score is roughly how many standard deviations is the prediction error away from what we would expect. So the prediction error has a certain value, and it has a certain covariance associated with it. So we kind of measure the prediction error in terms of the covariance associated with it. And we expect those to be, we expect the prediction error to be roughly between plus minus 2 standard deviations. And if it's much larger than that, it means that the model saw some data that was unexpectedly large or unexpectedly small. And we will use that eventually to figure out if we have a fault in our sensor or if the system is behaving strangely. All right, no matter if we have missing data or not, we always call the prediction step. So if we have several missing data points in a row, we just perform prediction, several steps prediction without performing any correction. But once we have data again, we start applying the correction. All right, and here I just create an array of empty inputs since this system doesn't have any control inputs. Since the data was very long, it was about 100,000 data points. I don't want to plot all of those because we will not be able to see much in the plots. So instead I plot a much smaller number here, n. So I perform filtering using the Kalman filter and the input data here. And I perform filtering over n samples of the data. And I will start at a particular start value that is controlled by a slider we will see and adjust later. And when I'm done with that, I get the solution, and I also get an array of these C-scores that we will use for fault detection. And one field of this solution structure is called LL for log likelihood. So the Kalman filter computes the log likelihood while it performs the filtering. And we will use this value later to optimize some of the parameters of the filter. Try to maximize this number. All right, before we plot anything, we will also perform smoothing. All right, so what does that mean? When we filter, it means that we estimate X at the current time step K given measurements up to and including the current time step K. All right, if we instead say prediction, then we estimate X at time step K given past information only, so not the information available at the current time step. We can also predict further in time if we would like that, but this is a one step ahead prediction. Smoothing, on the other hand, is computing an estimate of X at time step K given all the data up until the final time point. All right, so this is, you can of course only do this in an offline manner, and since we have a CSV file with all the data, we can do that here just for comparison, because it's interesting to compare the different behavior between the smoother and the estimator. But if we run something online, we can of course not compute the smoothing estimate. So this is just for, because it's interesting to look at. Right, so I compute the smooth state trajectory and covariance trajectory here also. And now we'll have a look at the result. So here we have our two state variables in top. So we have the one corresponding to temperature, so we see that it follows the measured data quite closely. And then we have the Z variable that corresponds to the kind of the velocity, if we look at the double integrator model as a particle with Newton's law governing it. Then this would be a velocity state. So it's kind of the slope of the first state variable. So when the first variable is changing rapidly, we see we have a large slope. And when it's not changing very much, we have a smaller slope. All right, and here in the bottom left pane, we have the data points in red, and we have the predictions in yellow dash, and we have the smoothed estimate in green. So we will zoom in here to look a bit closer. So here we start by seeing that there appears to be a number of missing values here. We can also see it here in the state estimate. We see that the covariance grows here, and that's because there is no data points available here. And then as soon as there becomes a new data point available, we see that the covariance drops because now we have got a new information. And then there are a bunch of missing points again, and the covariance grows. And once we get a new data point, we drop the covariance again. And down here we see that in between those data points there are many missing points here. The prediction just more or less stays flat here. And then when we get a new data point, it jumps rapidly. Whereas the smoothed estimates, so the smoother is allowed to look at the future also. It can determine that, that probably the temperature was decreasing here between these 2 points. But the filter doesn't know that. It hasn't seen this point when it tries to estimate these points in between here. All right. If we look at the interval between the second and the third point, we see that the filter is kind of estimating a downward slope like this, right? And that's because it has this second state variable as well. It kind of extrapolates here using if you imagine an arrow pointing between these 2 points, it thinks that it will continue on the same kind of trajectory. But then when we get the data point here, we see that, oh no, that was incorrect, so we need to adjust our estimate. And the smoother, which once again, which can look at the future, it does a better job here predicting this data point. And then it continues a bit like this here. So we can look here, it looks like we have a bit denser sampling. And we see that once again, the smoother is following the data points quite closely, whereas the predictor, the filter has this jagged appearance. All right, so if I move the slider slightly, I have said here that I'm going to move to 31K. Let's see if I can find that here. Okay, so what do we see here? Here there is a large gap in time where there are many missing data points in a row. And we see that the covariance estimate here for the first state, it really explodes. So that means that as time goes and we have no measurement, we get more and more uncertain about what the actual temperature is. And we see that this one says that the temperature could have reasonably gone up to 200 and down to -200. So we perhaps know that that's probably not reasonable, but that's what the current model thinks is reasonable at least. And then when we actually get some measurement available here, we see that the covariance decreases very rapidly again. And if we look at this plot of the output predictions, we see that the filter here, it just extrapolates from these points down. And then it makes a huge jump when we got new data. So we see why it extrapolates down there. It's because the very last data point was kind of a large decrease. But the smoother says, that's probably not reasonable. We saw that we were having a downward slope, but then we get a point up here, so there's probably some kind of trajectory like this in between. All right. So this is what the model thinks. We have no data, so we can't actually tell what is correct. All right. So if we go to 42K instead, we see that there is some kind of a large outlier here. We can look here maybe. We see that here suddenly the temperature does a very rapid drop, and then it goes up again, and we see that the filter finds that okay, but the smoother kind of, yeah, that doesn't seem reasonable according to the current model, so it kind of smooths over that, assuming that's kind of some outlier or some large measurement noise or something like that. All right, so this is kind of how the filter and the smoother behave. Let's see now. I will drag these sliders with me down so I have them for the next plot. I say here that before, when we designed the filter, I picked a covariance matrix by tuning and looking in a plot. So that's not very principled. We can use a much more principled approach to figure out a reasonable value for the covariance matrix. And here we will approach it as a maximum likelihood estimation problem. So I said that the Kalman filter computes the likelihood of the data given the model. And we can use that and optimize that to find the best value of a parameter. We can optimize more or less any parameter of the Kalman filter using this approach. And here we will just optimize kind of the scalar multiplicative factor that multiplies the double integrator covariance matrices. And since this is a scalar case, we have only a single parameter we want to estimate, we can compute the log likelihood for an array of covariance parameters and then plot the result. So that's an easy way to optimize a scalar function. And I do that here. I say I want to try with the covariance values between 1e-5 and 1e-2. And I want to try 30 different values. And then I just map over this array of values and I compute the covariance matrix. So it's the double integrator covariance scaled by this parameter I'm optimizing. And then I put this covariance matrix into the Kalman filter and I perform the filtering and I return the log likelihood. So now I have a number of different values here. So the x-axis is my parameter and the y-axis is the log likelihood. So we see that somewhere here in the middle there is a sweet spot where the likelihood is the highest. And we can extract that and it gives me this kind of value. So it's slightly different from what I picked before when I just picked a value. So if we would like, we could use this value and then perform the filtering again, and maybe we will get a slightly better result. But we will actually take this a step further. So here we optimized only the covariance matrix. We could actually optimize not only the covariance but also some parameters of the model at the same time, and we will do that here. So I said that we used a dynamics matrix that looked like this. So this is a double integrator covariance matrix. And maybe this is not a perfectly reasonable model. Because what does this mean? It means that if we don't get any data, it will just, the temperature estimate will just continue kind of in the direction it was heading. And that means that if we don't get the data for a very long time, then the temperature estimate might increase to quite unreasonable levels. All right, so how can we mitigate that? One way to mitigate that is to introduce some damping. So if we introduce, say that the velocity in the next time step is not equal to the velocity in the current time step, we say that it's some factor alpha times the velocity in the current time step. So if alpha is chosen slightly less than 1, then each iteration the velocity will decrease. And eventually it will decrease all the way down to 0, and that just means that the temperature estimate will stay flat. It will not continue to increase or decrease. So we will let an optimizer find the best value of alpha for us. And if we use this kind of model instead of the double integrator, the pure double integrator, then we can't use the pure double integrator covariance matrix either. So we'll optimize the full covariance matrix of this system. So before we had one parameter that affected the covariance matrix, and now we will actually have the entire covariance matrix. But a covariance matrix has a number of constraints associated with it. So even though it has 2x2 parameters, 4 parameters, it also has the constraint that it must be symmetric and positive definite. So that means that it's enough to estimate one triangle of the covariance matrix. So that's 3 parameters. And since it has to be positive definite, what we actually do is we estimate not the triangle of the covariance matrix itself, we estimate the triangle of its Cholesky factor. And if we take the Cholesky factor and multiply it by itself, we get something that is always positive definite. So that's kind of a nice way to enforce that constraint at the same time. So I have a little helper function here that takes a parameter array and constructs this triangular matrix. And I also have the inverse function here that takes a triangular matrix and extracts parameters from the triangle we're interested in. And then my initial guess will be the Cholesky factor of the covariance matrix I picked above. And then for this velocity, or this kind of damping term, I will just pick value 1, which is what we used above, and let the optimizer find something reasonable. And since this has to be positive, I would have to enforce, and it should also be ideally less than 1. But since it has to be positive, I would have to enforce that the optimizer doesn't pick negative values. And one way of doing that is to optimize the log of the parameters instead. Because then the optimizer can pick any value, and then I compute the exponential of that value, and then I get a positive number. So that's kind of a neat trick to ensure that you always have positive values. So my initial guess is this vector, the logarithm of this vector, where I have the triangular entries of the Cholesky factor and this 1 corresponding to the damping term there. Then I have a helper function that takes a vector of log parameters, exponentiates those, compute the Cholesky factor of the covariance matrix. Then I compute the covariance matrix, it's the Cholesky factor times itself. And then I add a small amount of numeric regularization here to make the problem a bit simpler. And then I construct the dynamics matrix. It's 1, 1 still in the first row, and then 0, and I call this the velocity parameter. It's the 4th parameter in my optimization vector. And if that's greater than 1, I return infinite. To this kind of a quick and dirty way to enforce that the optimizer doesn't pick a value greater than 1. Then I package this into a Kalman filter, and I use that in my cost function. So the cost function is simply pass the parameters into this get optimizer Kalman filter, and then perform the filtering. And then since we want to do maximum likelihood, and the estimator minimizes the cost function, we return the negative likelihood here. And if somehow an error occurred here, an error can occur if we get a nonce, or if we get a covariance matrix that is too numerically so even though I use this trick to enforce that it's positive semi-definite, we can still pick a value that is 0, and that means it's semi-definite, and then the Cholesky factorization inside the filter will fail. And if that happens, then I just return inf, saying that's not a good solution. So we can test my cost function with the initial parameter vector, and it returns something. So this is now the negative log likelihood. And then to optimize this, I load a package called Optime. It contains a number of simple optimizers. I will optimize my cost and my initial guess of the values is this params. I will use the LBFGS. It's a gradient-based. Let's see here. It tries to approximate Hessian information using just gradients. So this kind of traditional optimization technique. And I will use automatic mode forward differentiation to derive the gradients. I don't have to derive the gradients here. Automatic differentiation will do that for me. And we see that it takes about 10 iterations, and it started at some value here, and it gave me some slightly smaller value here. So we see that these are negative, so it has decreased the value slightly, and it took about 3 seconds. And then we can see what value it found. So we started with the parameter R1. This is what I had guessed, and this is what the optimizer returned. So we see that it's slightly different. Another way to look at it is that here was my initial parameter vector. So this first 3 entries are the triangle of the Cholesky factor of R1. And the last entry is this velocity parameter. So we started at 1 and we got some slightly smaller value with some damping. So this means that the velocity will kind of decay over about 10 samples or something like that. So we can now perform filtering using these optimized values. So to do that, I will grab the slider I had. Sorry for the scrolling. This slider controls all the plots in the notebook. All right. So we will go back to, or we can stay here. So now I show the same plot as above, but I've also added some vertical blue lines in this plot here, and these indicate outliers. And we will look a bit further on how I computed those later. But now we see that what I previously said here, there was a strong dip here. We can now look that the filter has detected an outlier here. Okay, so this was an uncomfortably large change for the model, so it considered it an outlier. All right, so how did I compute this? How did I figure out that this was an outlier? To do that, we will enter the kind of a section of the notebook I call fault detection. So I said before that when we do the filtering, I compute also the z-score. So the z-score is roughly the number of standard deviations my prediction is away from what was expected. And here I plot the entire array of z-scores, and we see that most of the time they are quite low, but sometimes there are kind of large spikes. And I've indicated here with the dashed lines 1 standard deviation away, 2, 3, 4, and so on. So we will say that anytime the z-score is larger than 4, so anytime the prediction is more than 4 standard deviation away from what was expected, we will indicate an outlier. So we see that there are a number of outliers detected using this method here. All right, and that's what I plot in the figure above here. So here on this little, let's see if I can reset the plot. Yeah, on this little interval, it has detected a number of outliers, and we can zoom into those a bit to see and see if we can understand why. So here we see that the model, the temperature changes quite slowly, and then suddenly it makes a huge drop and then back up again. And the model says that that's very unlikely to happen given the model. So there must be something wrong with this data point. And it could either be because the sensor was a bit faulty. It could also be because the temperature dropped for whatever other reason. Maybe someone, I don't actually know what kind of thermal system this data is coming from, but say that someone opened a window and it got suddenly very cold. All right. So we have something fishy here, and if this corresponds to some industrial process, maybe this an alarm should go off, and we should a person should have a look at this and see if there is a problem with the process. All right, and the same happened over here, that there is something going on. There is a data point here. There is just too different from the others. It was too unexpected that this happened, so it flagged it as an outlier. All right, I have a few more data, a few more time steps I would like to go to. So 61K. Let's see if we have something interesting going on there. All right, so this is the point in the data set where suddenly there was a huge jump in the temperature. This is most likely a series of outliers, right? So the temperature was between 0 and 40 degrees. And then suddenly it jumps from about 20 to well over 140 here, 150. And we see that the prediction of the filtered estimate, it just stays constant here. So now when we have, before we had a velocity term that would have just caused the filter to extrapolate like this. But now we see that the filter kind of increases its prediction slightly, but after a few samples, the velocity dies down because this damping term, and we have a constant prediction. But this, and that constant prediction stays until we get this data point up here. And the filter flags that as an outlier because that's very unreasonable that would happen. But the smoother, on the other hand, has seen this data point, so it knows that, yeah, it must kind of be some line connecting these two here. So the smoother figured that out. But the filter has nevertheless said that this is an outlier. And why is that? Because if we look at the covariance here, we see that the covariance, it does grow when we don't have any data. But then when we get this data point, it's still well above what the filter considers reasonable. So the filter considers something in between these two bands here reasonable, but it got the data point all the way up here. So that's unreasonable, and it says that must be an outlier. All right. Let's see if we have some more interesting data points. We're going to go to time point 74K here. Let's see if we can reset there. Here we have a number of quite wavy patterns in the measurements, and we see that the filter has flagged a lot of outliers here. So we can try to see how these look and why that is. So we see that we have kind of a smooth change in temperature here, and then suddenly there is a very rapid increase in temperature. And then after a while we have a very rapid decrease in temperature. And the filter, which is not okay, which with such large changes in kind of the slope, it says that this behavior looks very strange. And it almost looks like we have a different kind of dynamics governing the system here for a little interval before it goes back. And then that happens over and over again. And this is kind of an isolated sequence in the dataset where this happens. So there appears to be something different here. And if this is reasonable, if we look at this and determine that no, there is actually not a fault happening here, this is expected operation, then we would have to tweak our covariance matrices or maybe even the model so that this becomes more likely under the model. But under the current model we have, with the choices of covariance matrices we have made, this is unlikely to happen, and it has flagged it as outliers. We're also going to go to one last data point here to have a look if there is anything interesting. 112,000. All right, here. So what do we see here? We're going to zoom into, I believe, this little section. So here we see that there is a kind of a large gap of missing data. And if we look at the predictions made by the filter in the dashed yellow line, we see that it extrapolates upwards, but then the velocity decays after a while, and it says, now I feel uncomfortable extrapolating too far, so let's keep the prediction constant. And then the new data point came, and it had to make a large correction. If we had not had numerical damping, we would probably have continued the extrapolation up here, and it would have been better in this case. But the optimizer figured out that over the entire data set, it's probably better to have some numerical damping than to have none, like we had before. So that's kind of a trade-off the optimizer has made. All right. So as a final step, I would like to also see, is it just that the model says that there is an outlier, there is a large z-score whenever the velocity is large? Okay, so maybe if we did this outlier detection in a very naive way, we might look at the slope by just differentiating the data and say if the slope is too large, we detect a fault. But here we see, here I plot velocity versus z-score. So velocity is the slope of the temperature data. And we see that there doesn't appear to be any correlation. So that would have been a very bad way to detect outliers in this case. because the temperature isn't, the slope of the temperature doesn't change infinitely fast. So with the model that has this additional state variable, we can kind of adapt our slope, adapt the second velocity variable, and only if that one changes very rapidly, then we detect an outlier. So whether that is reasonable or not, of course, depends on your system. But it appears to work reasonably well for this data set. All right, so as a summary, we have used the state estimator, and we have used it to indicate fault when the error is larger than expected. And what does it mean for the error to be larger than expected? Well, expected is under a certain model, right? The model expects the system to behave in a certain way, and if the prediction error using that model becomes large, then we have flagged a fault or something is strange. So in a future video, we might use a more sophisticated model. So here we just used a trivial model that was inspired by how temperature is changing in the system. But we might use, imagine if we have an HVAC system that is controlling the temperature in a building. Then we can't only measure the temperature, we also know some aspect of what thermal energy we put into the system. So if we run the HVAC system on high power to produce heat in winter, then we know that, and then we shouldn't be surprised that the temperature is increasing rapidly. And on the other hand, if we detect, for instance, that someone starts a fan and the temperature decreases rapidly, we shouldn't be surprised by that. But if the temperature decreases or increases rapidly even without us doing something like that, then maybe there is a problem. And we can use that more elaborate model to do more sophisticated fault detection. But that's for a different video. Okay, thank you very much.